we're going to talk about symmetry of functions. And so once again, and it may not be always a function, but just symmetry of a graph. And when we talk about symmetry, this goes all the way back to geometry. We know that if something is symmetrical, it's the same on both sides, right? Like for instance, our bodies are symmetrical. If I were to draw a line right down the middle, got an arm on both sides, eyes on both sides, ears on both sides, and so our bodies are symmetrical. And there's a lot of different things in life that are symmetrical. And you might remember from like Algebra 2, sometimes we talk about the line of axis of symmetry, and we're going to talk about that some later in the semester as well, where we have a line that goes right down the middle of the graph that makes it symmetrical, especially for a parabola. But we're going to look at three different types of symmetry today. I'm going to kind of show you what it looks like graphically, and then we're also going to do it algebraically as well. Okay, so first up, I'm going to draw three different graphs up here. The first one is what we call symmetrical to the x-axis. If a graph is symmetrical to the x-axis, and this isn't something that we see very often, but that means we have the x-axis splitting the graph right down the middle. Okay, the x-axis goes right down the middle of the graph. One way that we know that this graph is going right down the middle, other than just visually looking at it, and it looks like it does, but to verify that it actually does, these 2 points are reflected over that x-axis. So these 2 points would be considered reflections of one another. So for instance here, I could say that this point is 2, 3, which means I go over 2 and up 3. To get to the other one, I would still go over 2, because this is 2 right here, but instead of going up 3, I could go down 3. And so when something is reflected over the x-axis or has a symmetry of the x-axis, then the y values will be opposite. It'll have the opposite y value. The x value will be the same, but the y value will be the opposite. Okay, so the second one we're going to look at here, and this is probably more familiar with one that we've seen before, is the y-axis. If I draw a parabola, okay, we're pretty used to seeing parabolas before. Let's say I give you a point once again at 2, 3. In order for this to be symmetrical, this point has to be reflected over that y-axis. That means that it's symmetrical to the y-axis. I can just reflect it over that line of symmetry. And so this point over here, instead of going right 2 and up 3, we would go left 2 and up 3. So that one would be flipped. It would be 2 to the left instead of 2 to the right, but it would still be up 3. And so what we notice here is that it would have the opposite x value. The x value will be the opposite. The y value stays the same. Okay, the third one that we're going to see is one that is symmetrical to the origin. In order to be symmetrical to the origin, first thing is it must go through the origin. If it doesn't go through the origin, it can't be symmetrical to the origin. So it has to go through 0, 0. But what's different on this one, once again, I'm going to use the same point to start with, just so you can kind of see the relationship all these have. 2, 3 is my starting point. if I wanted to come up with another point that would be on that graph, then I could pick out a point, like let's say down here. And this point here would be -2, -3. So in this case, both the x and the y's are going to be opposite. So we would say the opposite of x and the opposite of y. Whatever this original ordered pair is, these 2 points would be the opposite of both of those. And so really what's happening when I do the origin, we said on the x or the y-axis, I flip it over the y-axis. The x-axis, I flip it over the x-axis. For the origin, I'm going to flip it over the y and then the x, or you could go over the x and then the y, but eventually I'm going to reflect it over both axes, both the x and the y, and it doesn't really matter what order you do it in. And so that's why it's opposite of x and the opposite of y, because we're flipping it over both. Okay, and so that kind of shows you how you can graphically determine if a graph is symmetrical to the x-axis, the y-axis, or the origin. You have the possibility of sometimes it might be symmetrical to more than one, okay, and we'll kind of look at that today. There is a possibility it could be symmetrical to all three, and we'll talk about what that would look like as well. And you might find a graph that's not symmetrical at all. None of these would be. You might find a graph that's not symmetrical to any of those three. So you got a lot of different options there. So that's how we could do it graphically, is we simply just look at some points that are on the graph and look at the signs on those points and determine if it's been flipped or not. And we're going to do it algebraically. Now I'm going to start with one that's really easy, okay? And what I'll tell you here is if I give you a function like y equals x squared plus 2, I'm going to show you how to do it algebraically, and I'm going to show you why probably doing it graphically would be a piece of cake. And I'm going to wait and do that to the end and show you that. But sometimes I'm going to ask you to do it algebraically, because sometimes we're going to have to do it algebraically. We may not be able to put it into our calculator and do it graphically, and I'll show you why. So what we have to do when we do it algebraically is we have to check all three. Is it symmetrical to the x-axis, the y-axis, and the origin? And we're going to remember the rule that we talked about just a second ago. And that's why I like to start with the graph first. When it's symmetrical to the x-axis, we always do the opposite of y. And here's our goal. When we do it algebraically, we're going to put negative y in place of y, and we want to see if I get the same thing that I started with. If I do, it would be symmetrical to the x-axis. So negative y goes in place of y. And I'm going to try to get it back to the place where it was. I'm going to try to get y by itself. Well, if I try to get y by itself here, I would have to divide by -1 all the way across. And the question that you ask yourself, is this the same as what we started with? And it's not. It has different signs, right? And so our answer is no. It is not the same. So it is not symmetrical to the x-axis. If it is the same, then it would be symmetrical to the x-axis. Okay, for the y-axis, we do the opposite of x. And so kind of the same idea. We're going to put a negative x in place of the x. It replaces my x value. So we're going to go y equals negative x squared. Notice how I put the negative x in parentheses? It's a big deal because it's a negative. And when I square that negative, I want that whole thing to be squared. Because when I square a negative, it makes it positive. And so then once again, the question you're going to ask yourself, is this the same as what I started with? And this one would be yes. Exactly the same equation. This matches with this, the same equation. so it's symmetrical to the y-axis. Okay, that doesn't mean we stop there. We want to check all three. So then finally, the origin, and the rule that we talked about with the origin with graphing was it's going to be the opposite of both. So we're going to put in a negative x and a negative y. So it looks like that. Okay, order of operations, I'm going to square it first. And I'm going to divide by -1. And once again, is this the same as we started with? It has to be x squared plus 2, and it's not. Okay, so we would say that this is only symmetrical to the y-axis. Now that's a lot of work to get there, right? And the work is not really difficult work, but just kind of showing your work and showing what you're doing can be a little bit cumbersome. But what I told you is we can do a lot of these graphically. And if I think about or remember or at least know what the graph of y equals x squared plus 2 looks like, what kind of graph is it going to make? Yeah, it's a U, right? Because it's a quadratic equation. All quadratic equations, if they have x squared in it, it's going to make a U. This one is actually going to go up to, and you could put this into your calculator if you wanted to. And I'm just doing a real quick sketch here. But if you wanted to put it in the calculator, you could. Notice how the y-axis is splitting that graph right down the middle, right? This would have been a whole lot easier for me to graph it first and then just say graphically. The y-axis is splitting the graph down the middle. The y-axis is my line of symmetry. So this is symmetrical to the y-axis. It's not symmetrical to the x-axis because the x-axis does not split it. The origin does not because it doesn't go through the origin. And if I reflected a point, it's not going to end up in the opposite corner when I do the origin. So this is only the y-axis. Okay. So if you have the choice, of doing algebraically and graphically, this by far and away is going to be the way to go. Okay, is to look at it graphically and say, I know where the symmetry is going to be. Okay, but we may not always have that. Okay, so the next one I'm going to give you is going to be a little bit different equation. We haven't seen an equation like this yet. And so if I just said, prove what kind of symmetry this one has, if you said, well, I'm just going to go to my calculator, I'm going to graph it, can I put this into my calculator? Unfortunately not, okay? And even if you said, well, I'm going to solve for y, solving this equation for y is going to get a little bit messy and not really something that we're going to be able to do, okay? So using our calculator here and graphing this is not really an option right now, at least with what we know, okay? So this would be an option of the only thing that I really have is to try it algebraically. And we're going to go through the same 3 steps that we did just a second ago. We're going to do the x-axis, the y-axis, and the origin. Okay, and all you got to do is just remember the 3 rules. The x-axis is the opposite of y, the y-axis is the opposite of x, and the origin is the opposite of both. Okay, so when we plug it in right away, for the x-axis we're going to plug in negative y. Make sure when you put it in, you put that negative y in parentheses, okay? That's probably the most important step that we do here. And when I take a negative number and raise it to an even power, what's going to happen to that? What happens to the negative? It disappears. It becomes positive, right? just like when we did it earlier a few seconds ago with squared. If I square something, if I square a negative, it makes it positive, okay? That works for any even power. So if it's 2, 4, 6, 8, whatever, then as long as it's an even power, the negative will become positive. So x squared stays the same. This becomes y to the fourth. This is 5, okay? Is it the same as we started with? We would say yes. So this is symmetrical to the x-axis. Then I'm going to plug in a negative x. When I square a negative, it makes it positive. We get back to the original, so it's a yes again. The origin, we're going to do the opposite of both. Both of these will become positive. And so once again, it would be yes. So this one is symmetrical to all three. The x-axis, the y-axis, and the origin. Anybody got an idea of what a graph of something that is symmetrical to all three would look like? Circle, yeah. If I were to graph a circle, okay, it's not a perfect circle, but you kind of get the idea. The x-axis is split down the middle, the y-axis is split down the middle, and if I take this point here, I can reflect it over the x and the y-axis, and it would put it on an opposite point on the opposite corner. Okay. A graph that we haven't seen before, it's also called an ellipse. An ellipse is kind of like an elongated circle. Would be another graph. That could be symmetrical to all three, where the x-axis, the y-axis, and the origin are all going to reflect the same way. Okay. So there are some graphs out there. And those aren't really graphs that we're going to be able to put into our calculator and get a graph like that, but we're going to have to know that they do exist and that they're out there. Okay, the last thing that we're going to talk about is even functions versus odd functions. They're going to ask us, they're going to give us a function. They're going to ask us, is that an even function, an odd function, or is it neither one of those? Okay, an even function is always symmetric to the y-axis. So it would be like a parabola that splits right down the middle. An odd function is symmetric to the origin. So the way that I always remember it is odd and origin, O and O. Kind of a little trick to remember. And then obviously, if it's not even and it's not odd, then it would be neither. So one that is symmetric to the x-axis only, that would be one that's neither. and so it's kind of a different way of wording it, and it kind of goes off the degree, but I don't want to totally go off of the degree because sometimes that can be a little bit confusing because your graphs might look a little bit different sometimes. So we don't just always want to look at the degree of it either. Okay, so that's another term or pair of terms that they're going to use today. Is the graph even, odd, or if it's neither one of those, then you would say neither. Okay. There is a way to do that algebraically, but I don't really feel like we need to do that algebraically. I probably won't ask you to do that algebraically, so I'm not going to show you the algebraic part of that. Okay, that's all we got for today. Symmetry is pretty straightforward. Just looking at graphs, your calculator can be a really nice tool here to help you. think they're actually all on page 150, so you don't need page 149. So just page 150. I was thinking it was on page 149, but it's not. Some of them, they give you the graph, some of them they give you the equation, and then the last couple are your even, odd, or neither questions. On those last two, they ask you to do it algebraically, but I did not show you how to do it algebraically, so you don't have to do it algebraically. Just do it by plugging it into your calculator and seeing what the graph looks like. One question that you're going to see here is if I gave you a point like 7, 8 and ask you if it's symmetric to the x-axis, what would it be? Well, the x-axis, remember, is the opposite of y. So if my original point was 7, 8, then what would my new point symmetric to the x-axis be? I just have to do the opposite of y, so it would become 7, negative 8. We just have to do the opposite of the y by 8. Okay. If it was the origin, it would be both. So it's not going to give you an equation or a graph. It's just going to give you a point, and you have to apply that change to that point. So same idea, just with a point rather than a graph. But I wanted to show you one of those. I forgot about adding those to the notes.